Hello, welcome to NEF Center. Today we will talk about dimensional analysis. Physics can be viewed as the language of nature, where every physical law is written using dimensions. Newton's law of gravitation illustrates how mathematical equations describe natural phenomenon. Dimensional analysis provides a way to verify whether equations are physically meaningful by examining the dimensions of each quantity. The historical development of dimensional analysis explains that scientists sought a systematic way to describe physical laws independently of the chosen system of units. Dimensional analysis became an essential tool in theoretical and experimental physics as it saves projects from expensive costs and unnecessary errors. Measurement is the foundation of physics. Before any scientific law can be established, physical quantities must be measured accurately using standardized units. Every measurement consists of a numerical value and a unit. Without units, numerical values have no physical meaning. All physical quantities are built from 7 international system-based quantities: length, meters; mass, kilogram; time, seconds; electric current, ampere; temperature, Kelvin; amount of substance, mole; luminous intensity, candela. These quantities serve as the building blocks of all derived physical quantities. More complex physical quantities are obtained by combining the base quantities. Examples include velocity, acceleration, force, pressure, energy. Each derived quantity has a dimensional formula obtained from the dimensions of the base quantities. Examples: velocity is length divided by time. Dividing it more by time gives us acceleration. Multiplying it by the mass it gives us force, and so on. Adding ampere to these dimensions unlocks electromagnetism. Every physical quantity possesses a unique dimensional formula. Dimensions obey algebraic rules similar to ordinary algebra. Key rules include: dimensions multiply during multiplication. Dimensions divide during division. Exponents are added or subtracted accordingly. Only quantities having identical dimensions may be added or subtracted. Dimensional analysis can also determine the dimensions of physical constants. Examples: gravitational constant, G-force constant, and other universal constants. This helps verify equations involving constants. One powerful application of dimensional analysis is predicting the mathematical form of unknown equations. Example: determining the period of a pendulum from length, gravity without solving differential equations. The dimensional analysis procedure consists of 1. Identify all variables. 2. Write their dimensions. 3. Equate dimensions. 4. Group them by base units. 5. Solve for unknown exponents. This systematic process greatly simplifies many engineering problems. Applying dimensional analysis to a simple pendulum predicts T proportional square root L per gram, which is consistent with the exact physical solution. T equals 2 pi square root L per gram. Dimensional analysis correctly predicts the functional dependence but cannot determine numerical constants such as 2 pi. Every physically correct equation must satisfy the principle of dimensional homogeneity. 2 important rules are introduced. Only quantities with identical dimensions can be added or subtracted. Arguments of trigonometric, logarithmic, and exponential functions must be dimensionless. These rules provide a simple way to detect incorrect equations. Dimensional analysis acts as a diagnostic tool to detect incorrect equations. It can immediately identify equations that are dimensionally inconsistent, helping physicists and engineers detect algebraic mistakes before performing detailed calculations. Dimensional consistency is a necessary condition for any physical equation. If an equation is dimensionally inconsistent, it is certainly incorrect. As we see in the following examples, you can't add dimensionless number to units. If it is dimensionally consistent, it may be correct, but additional physical or experimental verification is still required for accurate results. This diagram shows the logic of dimensional analysis. We begin by checking whether an equation is dimensionally homogeneous. If it isn't, the equation is guaranteed to be false because the dimensions don't match. If it is homogeneous, the equation becomes a possible candidate for truth, but it still requires physical validation. So, dimensional analysis can prove an equation is wrong, but it cannot prove it's correct. That's all for today. See you next lesson.